Okay, off we go. So last time, wrong page. Here we go. Last time we had just started section 3.4. We're going to be pretty quick with this. It's kind of a introduction to plant some thoughts in your brains that will hopefully, digest over the next, month or so before we get to a real presentation of this stuff. So we talked about how you can take the gradient and kind of pull out specifically what is that thing by itself, and we argued that it is this thing. That's what we call the del operator, and we're going to do various different things with it. Okay, so the first thing we're going to do now, this is going to come out of nowhere. There's a good context for this. There's a good reason to make the following definition, and we're not ready to see that reason yet because we don't have the proper tools yet. But here's what it is. We're going to talk about this thing called divergence of a vector field. And divergence is computed by this formula. Comes out of nowhere. I've given you no reason to believe that this is an interesting object. Okay. What I will point out is you can see how this notation is already kind of handy, thinking of the del operator as itself being kind of a thing on its own, and recalling that the vector field has coordinates like this. This really looks a lot like a dot product. And so this notation of calling it a dot product, even though that's actually a little sketchy if you think about it, right? I mean, del is not really a vector. Dot product is defined as vectors. So this is sketchy, right? But as a notational shorthand, it's very convenient, and for reasons that are beyond what we're going to go into in this course, is actually really convenient in some very nice ways. So y'all are going to see that notation a lot, not just in this course, and so heads up. Okay, so what is this thing? What's the geometric interpretation of this? And again, we don't have the tools yet, so I'm just going to make an assertion and hope you believe me. And here it is. This is what divergence represents. Divergence, aka that notation. It's, roughly speaking, to what extent is the fluid flowing outward away from the vicinity where you're evaluating that divergence? Okay. So it's easiest to see what we mean by this with an example. And so let's look at this example right here. Here's a vector field. And by the way, exercise for y'all, make sure you can do this. Persuade yourself that this is a picture of what that vector field looks like. What you're going to notice in preparation for that is notice that the field vector, oh my gosh, looks just like the input point. To say that a little bit more carefully, the field vector is the position vector for the point where you're evaluating. Okay, and with that in mind, this picture, and again, think through how to connect those dots. Okay, so we compute the divergence. Now, specifically, I'm going to compute the divergence only at the origin. Sure, the calculation is equally easy everywhere, but I want, for the purposes of this example, let's focus our attention at the origin specifically. Right? At the origin, you compute the divergence, you get 3, which you'll notice is a positive number. And then reminded that what divergence represents is fluid flowing outward away from that vicinity. I ask now, just, does that track here? Right? Is the fluid flowing outward to a positive extent per the divergence I just computed? Is the fluid flowing outward away from the general vicinity of this point where I just computed the divergence? Well, yeah, sure it is. Look at it. It's flowing. It's clearly just flowing outward there, right? So this is the classic first example. This is the kind of the easiest. This is, in your mind when you see, divergence and what does divergence look like, it's something kind of along these lines. It's not always exactly like this, and it's not always this simple. But this is the classic first example. Okay. Now, I'm going to say a couple of quick words here about how to interpret this physically and what would be the the sort of the physical upshot of this. What in fact is represented by a fluid. What are the physical scenarios where we could have a fluid like this? And I'm going to point out there's a couple of them, and they're actually pretty different. Right? So my first example on this is, imagine that there's a bunch of birds at the top of a palm tree, something like that. Flock of birds. There's a million birds all in the same tree there. Tall tree, so they can fly every which way as needed. Tall tree, bunch of birds sitting there, and then something happens. A car backfires. They get scared and they scatter. Right? Something maybe kind of like this would be a reasonable expectation of what that would look like. So the upshot, though, is in this general vicinity, as the birds fly away, the bird density, number of birds per unit volume in this general area, decreasing because they're flying away, right? Of course. Does that make sense to everybody? Okay. So be careful with this, though. It's not always going to be the case that positive divergence means decreasing density. Here's a totally different metaphor. Perfectly reasonable. Maybe at this point, maybe I don't have a bunch of birds. Maybe I have a light bulb. Right? Well, if there's a light bulb there, then light comes shooting out every which way, just like we have in this picture. Well, something along these lines anyway, qualitatively. And, okay, so when you have a light turned on, we've got multiple light bulbs on in this class. Are these light bulbs depleting their supply of photons, right? Do they come with a, finite store of photons in there? No, not at all, right? That's just not what happens. Light bulbs do not have a store of photons. They create the photons. If there is an outward flow of photons, that is just representative of how much photons are being created by the light bulb. Everybody see the difference there, right? Now, again, it's the same kind of picture, but it's a very different physical reality. So I just wanted to point that out. So you don't want to. I got myself into trouble when I was y'all's age, and I was learning this for the first time, and this was in my mind. That's just the one picture that I had, and I had some other situations came up where I had to make sense out of things from this point of view, and it just seemed really wrong to me. And it took me a long time to kind of unwrap all of the bad intuition I had developed, and then sort of recreate good intuition. So make sure to keep both of these ideas in your mind. And by the way, just to make it more complicated, sometimes the physical scenario you're looking at might be a combination of both of these. All right? So if you are curious and want to talk about how might you, what sort of physically plausible situation is where this happens, come talk to me and I'll show you an example. Okay. All right. Next example. Vector field looks like this. Make sure you can do that, right, as always. Compute the divergence. Now this time you'll notice I'm computing the divergence at some point A. A could be any point. Now the calculation of the divergence, again, equally convenient everywhere. But in this case, I'm going to want to look at a different point other than just the origin. So we compute the divergence, and conveniently it's constant. It's always the same, so it doesn't matter where I'm evaluating it. Nevertheless, still answer is 0. Now, this might be a little bit counterintuitive. Let's think about a point like that. Let's think about this general vicinity around that point. I actually see an outward flow. Right? There's some outward flow like this. Well, how come I get 0 when there's clearly some outward flow? Well, it's because there's inward flow as well. And inward is the opposite of outward. And so when it comes to computing divergence, interpreting divergence, inward counts as the negative of outward. So this is net 0 divergence because there's just as much in as there is out. and it cancels. Yes?
What would a net non-zero look like?
Yeah, so like that.
Oh, okay.
Yeah. So here it's all outward. You could imagine a situation where maybe the inward is smaller and the outward is larger. Right, and maybe it just keeps getting longer and longer the further you go to the right. So yeah, here divergence would be positive, but still with some in and some out. Yeah. All right. Okay. All right. Next object that I'm going to define completely out of context and with no justification, just to plant the thought, just so these ideas can start percolating in your brains. So it's this thing called curl. Curl is defined by what I'm going to call this formula right here, and this again is more symbolic nonsense, right? It says determinant, as if that's a matrix. That's not a matrix, right? Or at least to whatever extent it's a matrix. I mean, are the elements allowed to be vectors? Weird. Are the elements allowed to be differential operators? This is really uncomfortable, right? This is strange stuff. But again, if you just interpret this in the only way that you could possibly make sense out of it and compute it up, it actually gives the right formula for this thing that we're calling curl. Now, that actual sort of expanded formula for curl I have never memorized ever at any point in my life. I've only ever memorized this formula because I'm no good at memorizing things. I am pretty good at noticing patterns, right? And this is an easy pattern that I can remember, but anyway. So I encourage you to remember this, but not the general formula. Okay. You'll notice as well, this is symbolic nonsense representative of a curl, right? That's in general how we write curls, and the first thing goes there, and then the second thing goes there. So this is actually pretty great notation to represent this symbolic nonsense formula. So again, heads up, you're going to see this notation. This is the most common notation that I saw in my physics major way back when, and I predict that y'all will see a lot of this in your engineering classes. Okay, again, why are we writing down symbolic nonsense? Well, I claim no justification, no context, right? All of that much of that will come later. I claim that this is kind of I have to be really vague and hand-wavy about this. To some extent, it represents kind of when I put air quotes around the term circulating, right? But it's like, imagine you have a fluid and it is kind of rotating, right? That the flow, as the fluid flows, is actually representing. Oh, excuse me. Oh, man, that caught me off guard. I'm not sick. So you imagine that the fluid is kind of rotating, right? That there's a sort of a rotational aspect of the fluid. This is what curl is actually measuring. So just again to get an example, not that this proves anything, right? But just to have an example that we can see what we're describing. Vector field, picture. Make sure you can do that. Right? Make sure you're comfortable with coming up with that picture. Let's compute the curl. Symbolic nonsense formula. There's the punchline, 002. So did this work? To what extent is this satisfying? Well, we pretty clearly have a rotational aspect of the fluid, right? I hope I can persuade you all that the fluid, per that formula for the vector field, this fluid is rotating around. And in fact, it's rotating around the axis defined by the curl vector. Right? So that's one of the two ways that curl describes the rotation. The curl describes the rotation by telling you what direction does the axis point that the fluid is rotating around. Is that cool? All right. Right. Okay. Now, while I'm at it, let me point out what about the magnitude? What is the geometric significance of the fact that the magnitude here is 2? And we're not going to talk about how to quantify that. That can be done. The problem is it's done differently in different circumstances. We don't need to. I'm going to say that's a context problem for whoever it is else in your future who will be doing curl, like whatever engineering class you might happen to take or physics class, and units and stuff like that can be quantified in that context. What I'm going to tell you, roughly speaking, is that the greater the magnitude, the more, in whatever appropriate sense, the more of a rotation there is. So if there's a short curl vector, then it's a slow, perhaps, rotation. If it's a long curl vector, then there's a fast rotation. The longer it is, the faster the rotation. So, all right. We're not going to be any more precise than that. Okay, another example, another easy one. Vector field picture, make sure you can do that. We compute the curl, we get 0. That suggests no rotation at all. And again, I'm going to say I think that tracks pretty nicely, right? I mean, if you were to look at this and try to ask, to what extent is the fluid rotating here? I don't see anything rotating. So says curl. So again, success. Yeah. Okay. Here's the weird one. This is subtle. I put this example in here specifically to combat a misinterpretation of what we mean by rotation of the fluid, circulation of the fluid. So here we go. Vector field picture. Make sure you can do that. By the way, before we get into the curl, notice that all of my flow lines are straight lines. I mean, coming at it initially, I don't really see any rotation there. All the flow lines are straight lines. Yeah, right? And yet, you compute the curl and you get not 0. Not 0 would suggest that there is a rotation in this picture. And again, this glance that we've given it so far kind of makes it look like there's no rotation. So who's right, who's wrong? Is the interpretation that I made, is that a bunch of garbage? No. There's a subtle rotation in the picture. So let me talk about what the subtlety is. If you go back to the very first example that we looked at here, there's kind of two sorts of rotation that we're seeing. On the one hand, you can look at the flow lines themselves, and the flow lines themselves here are curved and rotating, and that is easily mistaken for being what we're talking about, and it's not. What we're talking about is not how does one particular particle of fluid move, and does it move in sort of a rotating sort of circle. It's if I were to look at all of the fluid as a whole in a general vicinity there, is that as a whole rotating? And that's something that I claim is happening in this picture. And again, it's kind of subtle. Now I'm just going to zoom in so we can see a little bit better. Reasonable question. If I were to think about something sitting like that, what happens to it? Well, the fluid is pushing it, you might say, into the page on the left side, and the fluid is kind of pushing it out of the page on the right side. That'd be one way to say it, but do these cancel? No, they're happening in different places. Another way to say this is that this thing, whatever it is, I like to visualize a leaf sitting on the surface of a river, right? And that leaf just kind of floats and just kind of does whatever the fluid tells it to do, right? I feel like this leaf is being pushed, what I'm going to call clockwise on that side, and it's being pushed also clockwise on this side, right? So none of the flow lines have any curvature to them, but the leaf would rotate, and that's the circulation, that's the rotation of the fluid that we're talking about. So cool. Yeah.
Is that something we'll ever be able to tell from just looking at a picture, or will we always need to do the cross product?
I mean, in this case, you can kind of tell from looking at the picture, you know. I mean, not with complete confidence. Yeah, I mean, that's one of the things we like about curl is that it does this for us, right? And it is going to relate to another formula that we're going to talk about later on that we're not ready to do just yet. Yeah, we are in fact are going to write down an explicit formula for circulation itself, and we're going to get real precise about I don't want to say all, but most of what I'm saying here. But this is going to be a month and a half before we get to it. Yeah, sure. Okay. All right, so do keep this in mind when we're talking about the circulation of the fluid. Whoops, wrong button. Circulation or rotation of the fluid. We're not talking about flow lines. We're talking about, again, my favorite metaphor, a leaf floating around, and how does the movement of the fluid rotate that leaf or balloon or whatever it is in question. Okay. All right, now, last thing I'm going to do here, this is just to plant a thought, just to try to persuade you that there's a lot that's about to happen, and that there is something natural and fundamentally interesting about these operators. First thing I'm going to point out is you can compose them. And here's what I mean by composing them. If you, let's see here, color choices. If you talk about gradient takes a function and returns a vector field. Curl takes one of those vector fields and produces another vector field. And then divergence takes one of those vector fields and produces a scalar valued function. So the Legos fit together. You can talk about this composition. Green plugs into blue, which plugs into purple, right? Yeah.
Wait, what are the different ones?
Yeah. So this is gradient, right?
Yeah.
And this is curl. That's our new notation for curl. And this is divergence. Again, new notation for divergence. Yeah. Okay. So the fact that the Legos fit together is not the point here. Sorry, question.
Do the left be vector value and the right be scalar value? Like the final scalar value?
This exact particular composition is the one where magic good news happens. So the Legos will fit together in, like if you did divergence and then gradient and then curl, the Legos fit together, but it's just not that interesting. Nothing. It's just weird. Yeah, right. So this is exactly specifically the composition that we're going to be interested in. Yeah. Okay. So here's the shocking fact. And again, I mentioned this not because we're going to immediately do anything with it. We will do a lot with this later. But for the moment, I just want to raise some eyebrows and get you thinking, wait a second. How could that be? These things must be connected somehow. There must be deeper truths underneath what we're seeing here that we're probably going to be discovering soon, because all that's true. Okay, so here is the big fact that I want to point out. There is an asterisk. Disclaimer. We'll worry about that in a second. But disclaimer aside, all lifetimes are 2. Let me tell you what I mean by lifetime. Suppose you have some vector field that you then compute the curl of. Cool, you get some other vector field. Okay, fine. Whatever that vector field is, if you were to then compute the divergence, you would get 0. And I call this a lifetime of 2. What I mean by a lifetime is that this is the whole story for that thing. And what I mean by 2 is, think of each operator that we apply as representing the passage of 1 unit of time. It's just a metaphor. It's just a metaphor. Right? And then also I like to think of 0 as being death, kind of nothingness, if you will. Right? It's just a metaphor, right? But that's where the metaphor comes from. So every lifetime is 2. So this manifests in various different ways. So for example, and this is a true fact, if you take some function, take its gradient, to get a vector field, and then if you take the curl of that, you will get 0. You have to, because that is the lifetime of 2. Birth, survival, death. That is a lifetime of 2. So it has to be 0. Weird fact. And then here's the one that I find even more surprising, if you will. If you have some vector field, and if you take the curl, and if you get 0, well, that's death. Could this have been birth? No, it can't be birth. That would be a lifetime of 1. Everything has a lifetime of 2. That means this must have been survival. That means it must have been born here. That means there is a function whose gradient is that original vector field. If you have a vector field, if the curl is 0, that is a gradient of something else. Also true fact, yes.
So I'm assuming we can't go from, say, gradient to divergence.
Yeah, that's right. Yeah, this diagram fit together in exactly this way is all very, very delicate. Yeah, that's right.
So it's not cyclical.
I'm sorry?
So like you can't.
Correct. Yeah, no, you can't loop back. Yeah, no, I hear you. Yeah, no, it doesn't. Yeah, it's just exact. In my metaphor, the universe ends. Time ends right here. Right. Everything dies after that stage. Yeah, yeah.
So does that mean we can make the conclusion that if we're given a function, we know that its curl will be 0?
If you're given a function, you can't apply curl. Right? If you're given a function, you can take the gradient.
Right.
That gradient will have its curl equal to 0.
So, but if, let's say we're asked the gradient of this function.
Yep, so you have a function, you're asked to compute the gradient, you'll get something.
Okay, and then we know that thing will have a curl.
That thing,
0.
its curl will be 0.
Okay.
That's right, yeah. So, okay, now this is a really weird kind of little truth here, right? I mean, that's strange that something like this could possibly work out. And again, I hope this persuades you that even though divergence, if you think about the physical metaphor for divergence here, this is about, outward flows, and curl is about rotations, and gradient is about what direction is uphill and stuff like that. These operators are very powerfully connected to each other. Yeah.
So if the final value of the y is not 0, that means that the previous one is not a curl of anything?
Correct. That's another example of a lifetime of 2 argument. So if you have some vector field, if you take the divergence, if it is not 0, then there is no way that there is what one might call an anti-curl. Can't be an anti-curl because it would violate the rule. Yeah. Okay. All right. So again, now we're gonna do a lot of stuff with this later on. It'll be chapter 7, 6 and 7, mostly 7. So let's not get bogged down in this for the moment. I just wanted to plant this thought. I wanted to raise a couple eyebrows and convince you that weird stuff's going to go down in about a month or so. Okay. All right. So cool. And we are done with chapter 3, and we move on to chapter 5. Hey, wait, what happened to chapter 4? Let me go back to the content syllabus. And remember, we finished chapter 2, then we went into chapter 3, and now, as indicated here, we're going into chapter 5. So we are not skipping chapter 4 entirely. We're just doing it at the end of the course. Here it is. Chapter 4 is coming, right? Now, just so you know, why are we doing this? It's because chapter 4 is kind of a digression. It's not in the prerequisite trail to chapters 7, 6, or 5. And it's important, and you need to know it, but it can wait. And so the related note I should point out is that this stuff here, chapters 6 and 7, this stuff is challenging and requires time to soak into your brains. You need time to kind of get accustomed and kind of digest and just kind of get familiar with this stuff. So it's best to do this stuff as early as possible. Unfortunately, these chapters material uses most of the material from earlier in the course. So I can't start with Stokes' theorem. just can't do it. We don't have the tools yet, right? So chapter 4 is an easy section, easy chapter to just delay until later. Kind of costs us nothing. It has the benefit that it allows us to get to chapter 6 and 7 earlier, which gives y'all more time to digest those ideas. And that's the strategy there. Okay, let's talk about integrals. Y'all remember partial derivatives? Remember we started with partial derivatives? And then eventually we made other constructions. We figured out this thing called the gradient, really kind of a more sophisticated, more powerful idea. And then at some point we wrote down the derivative matrix. And ultimately we had to recognize that the derivative matrix really deep down, that's what a derivative is the matrix that takes input vectors and turns it into output vectors. That really is kind of the cornerstone concept of multivariable derivatives. But we started with partial derivatives. And again, why did we start with partial derivatives? Well, because it was easy. We were going to need to do it anyway. It's a nice little foot in the door, puts one in the win column for us, right? It was just kind of handy thing to start with. And then I gave you all a warning as we were doing partial derivatives. Don't get too comfortable with partial derivatives. It's a thing. It's useful. We need it, but this is not deep down fundamentally, 10 years from now when you think about multivariable derivatives, partial derivatives are not what I hope you'll think of. I hope you'll think about the derivative matrix. Okay, so we're going to do the same thing with integrals now. And I'm going to start with a certain point of view on multivariable integrals that we're going to need, and it's going to be useful for computations, and that's all well and good, but deep down, ultimately, this is not the right point of view. So again, same warning, don't hang your hat on this point of view. Think of this as a naive first attempt to get one into the win column, and we're going to see a much better idea. Not tomorrow, Wednesday. All right, so disclaimer aside. Y'all remember this story? If you have an area and you rotate it around the x-axis to generate a volume, and you want to compute that volume of this, what do they call it? A volume of revolution, I think they called it when I was in school. The way we do that, the way we compute it, is we slice it. And we look at those slices, and we argue that the slice is an area, which is easy to compute. That's the area of a disk, right? This is pi r squared, no big deal. Area times thickness, like so. Everybody remembers this? Okay, cool. All right, now we're going to try to answer a similar but different question. So here, let's suppose we're looking at a surface, and not just any surface, but a graph specifically of some function of two variables. And suppose I want to compute a volume. Again, this time it's not a rotated volume. This time it's the volume sitting under that surface, and specifically, let's see here, volume under, sitting over a particular rectangle. And so, man, you got to imagine some rectangle down here in the domain, like that. And how would I compute this volume under the graph, over the rectangle, as I have drawn in yellow there? Does everybody see the question? All right, well, look, I mean, naively, we could give kind of the same first attempt. We could say, okay, well, I can look at the volume of one little slice there, and I could ask, can I write down what this thing here is? And here's where I run into a problem. What is the cross-sectional area here? Is it a disk? No. Is it a square? No. Triangle, rectangle. Is it any sort of garden variety geometric figure that I can just write down the formula for? No. So we're dead in the water, and a lot of people would throw up their hands and give up. Everybody, right? I mean, right? You can think back to when you were in Calc 2. You wouldn't have known where to go from here. Well, it turns out we're actually in a great position. We just need to push forward. And here's the reality: that area that we're interested in here, that's the area under a particular curve. That curve is part of the original surface that we were looking at that had this equation. So that equation applies to that curve. If I want to compute the area under a curve, I mean, well, that rings a bell, right? How to compute the area under a curve? An integral or something, right? And in fact, yes, I can compute that area just by making sure I understand what, colored choices, whatever this height is here. I need to be able to write down height times length, I guess. Well, that height is the z coordinate of that point. Z is f of xy, so that height is f of xy. So, in fact, no problem. And let's see, by the way, I need to know that, pencil mode. I need to know that we're moving across the sort of the base of this area that I'm interested in. So x is going to need to go from a to b, it would seem. So integral as x goes from a to b. Boom, there's our area. Yeah.
What if like the curve, the inner curve is not the same across the whole?
You're talking about what if this wasn't a straight line?
No, I'm saying like what if when you're adding up those little sections?
Yeah.
What if all those little sections are not the same? Does it matter?
I'm not quite sure I understand what you're asking. So this curve is not going to have a constant height, right? The height is kind of higher in the back, and then it's kind of lower in the middle, and then it starts to go back up again on the edge.
I understand that.
Okay.
I'll ask you back.
Okay, fair. Okay. Yeah, okay, so I claim that if we're interested in computing this area, just to highlight it accurately, that area that we're interested in, that area is itself an integral. Yes?
Is it possible that we would have a curve that has 3 dimensions? And how would we, where we can't set it equal to z?
The whole premise here is that we start with a surface that is a graph. And so height is the value of the function for every point on that entire surface. And if it's true for every point on the entire surface, well, this curve, of course, is part of that surface.
But if the graph could the graph have 3 variables?
We're looking at this very narrow particular,
okay.
Yeah,
okay.
Right, yeah. So I mean, I like the instinct to, hey, let's generalize this, right? And we will eventually, but we need to get one in the win column here first. We're going to focus on this very specific setup. Yeah. Okay. So now I have a worry. Perhaps you do as well. Something I'm a little uncomfortable about. Certainly when I first saw this really bugged me. This integral right here, I mean, I've seen lots of integrals dx, but I've never seen one where there were 2 variables in the integrand. Right, so what's up with that? Can you have 2 variables in the integrand? Is that okay? What do you do with the y? Do I have to treat y as a function of x? Or how do I deal with this y when this is a dx integral? And there's actually a very crisp answer to this question. This is really important to keep in mind. Here we go. That the purpose of that integral is to compute this area. What area? Just to be explicit, the area for a particular fixed selected, right? You've got to tell me what y is before I even know what cross-sectional area you're talking about. So y has to be fixed to even ask the question, So as we answer the question by computing this integral, that y I get to treat as a constant because it is literally constant for the entire area that I'm computing. And so inside of this integral, there aren't two variables. Y is a constant. No problem, no concern, right? This is not a multivariable integrand. This is a single variable integrand. Y is like 6. Yeah.
How is y constant again?
Well, yeah. So I mean, our goal was to figure out what this cross-sectional area is, right? Now the cross-sectional area is going to depend on which cross-section you're looking at. So if you come to me and say, "Hey, compute that cross-sectional area," I'm going to say, "Which cross-sectional area?" You're going to tell me which value of y you're interested in. Now y is fixed. Is that cool? Yeah. Okay. All right. Now it's one of these weird things though, because you come back over to here, this cross-sectional area obviously depends on y, so y is going to vary, right? But y will vary for a while, but then once you need to know what a particular cross-sectional area is, then we have to fix y, and as we move in the x direction to compute that cross-sectional area, at that point y is a constant. So it plays two different roles in two different circumstances here, yeah.
Can you do the same keeping x constant?
Yeah. So right, I'm slicing, you might say, perpendicular to the y-axis here. Yeah, you can do it the other way. In fact, we'll get to that in a couple minutes. Yeah. Yes.
Can you have a surface that is not like you can't slice it perpendicularly, so you kind of have like a above y-section and an x-section, that would work.
I didn't quite understand. I'm sorry.
Y is not variable. For example, would you?
Again, we're just going to stick to this very narrow, exactly this setup. So we have a continuous non-negative function of x and y. We look at the graph. We have a picture that looks like this. Yeah. So we just want to stick with this for the moment. Yeah. Okay. So yeah, it's kind of all over with the shouting at this point. We wanted to compute the volume. Well, the volume was an integral. I mean, just like in this case. The volume is an integral. The integrand is the cross-sectional area. So, okay, our integrand is that cross-sectional area. And it's a little bit weird, but nevertheless, the answer then to our question, volume, is an integral of an integral. And this is called an iterated integral. This construction where we... in this case, we got to it by way of this kind of slicing process is how we answer that question. Yeah.
Can it be called a double integral?
I prefer not to call this a double integral. Some people like to call it a double integral. I'm going to use the term double integral for something else. It will then eventually turn out to be the case that those two things are very closely related. For the moment, I think it's important that we maintain that distinction. Yeah, so for the moment, this is an iterated integral, and if you've heard of a double integral, for the moment, that's not what this is. Okay, distinction to come later. Whoops. Okay, so a couple of things to say about iterated integrals, and then we'll do an example. So let's talk about the terminology a little bit first. We started off by slicing perpendicular to the y-axis and asking questions about what the cross-sectional area was, and then multiplying by dy and adding it to get volumes. I'm going to call that the dy integral, and you'll notice that's on the outside in our iterated integral. And then there's this dx integral. The dx integral is what we do to figure out what that cross-sectional area is, right? So how would I distinguish between these without using the names, dx and dy? And what some people like to do is talk about the first one and the second one, and I think that's a problem. Here's why. We wrote down the dy integral first. Then we wrote down the dx integral, so it's going to be tempting to call the dy the first integral and the dx the second integral. That's how we wrote them down. Now let's think about how we would compute them. And we're going to do a computation in just a second. When it comes time to compute this thing, we can't compute the dy integral first. I don't know what its integrand is. The dx integral is the integrand. I don't know what to do until I've computed the dx integral first. I can't even start computing the dy integral. That would have to be second. So this term, first and second, that's ambiguous. It really could go either way. It's just not clear what that means. So please don't say first integral, second integral. It doesn't mean anything. However, you can totally talk about the inside integral and the outside integral. And you just have to remember that when it comes time to compute, we integrate from the inside out. When it comes time to set up the integral in the first place, we set it up from the outside in. Okay. All right. Okay, next thing to make sure you remember. That inside integral. Don't forget that inside integral. Coming back to the picture, the inside integral represents this area. For which purpose? Y is a constant. Has to be constant because it's got to be settled before I even know what area I'm trying to compute. And notice that y that is a constant is the outside variable. So coming back down to here, for the purposes of the inside integral, the outside variable is a constant. This is a really nice way to remember it. We will eventually be slicing in the other order, and you don't want to have to remember, okay, so all the cases, and if the dx integral, if that's on the inside, then which variable is a constant, but in the other order, it's easy to get lost. Whichever integral is on the inside, the outside variable is to be treated as a constant. That's always going to be the case. Okay. All right, let's do one. Plug and chug. Okay, so again, suppose we want to compute the volume under a graph of a particular function sitting over a certain rectangle. I'll come back and talk about how to interpret this notation just a moment. Let me let's for the moment I claim it's this. We'll come back to that in just a quickie. I just want to get partial progress of the solution on the page first. We've been asked to compute the volume under a graph over a rectangle. That's what we just figured out. We already know the answer to this question. The answer, volume under a graph, blah, 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 iterated integral. So the very first thing I'm going to do in this question is say, oh, you want to know the volume under the, okay, boom, iterated integral. That's the answer. We've already reasoned it through. We don't need to reinvent the wheel on this. There it is. Everybody good? All right. Let's talk about this notation real quick. It's very convenient to use this notation to represent this rectangle as follows. The first interval tells me the range of values of the first variable, in this case x. The second interval tells me the range of values of the second variable, in this case y. And so if you think about, okay, all the points that have an x coordinate over here and a y coordinate in here, this is the rectangle that does that. Right? So very handy notation. Make sure you're familiar. Make sure you're comfortable. Make sure you remember how that notation works. We'll be using that a lot. The computation is very plug and chug after this. I want to call your attention to two things. First of all, it is very easy to mess up the integral. I know y'all know the integral of x squared is 1/3 x cubed, right? Old news. Single variable calculus. Y'all remember all that? You would think the integral of y squared might be 1/3 y cubed. It's not. Landmine. Heads up. This is going to be your job to make sure to watch out for the following. When you're doing the inside integral, which we are, the outside variable is constant. That means that y is a constant. That means y squared is a constant. And the integral of a constant is constant times variable x in this case. Is that cool? That's the first landmine. The other landmine, and I'll be quick about this and we'll call it a day. Just be real careful when you're plugging in. I've made the following mistake more than once. We're all fallible. I don't want you all to make this mistake too and lose points. When it comes time to plug in, a lot of people will just write down just the 1 right here because that's how you do it in a single variable calculus class. Because you don't need to specify what variable you're plugging in for in a single variable calculus class. There's only one variable. So you plug it in for of course, the only variable. What's the problem here? Here we have 2 variables. You've got to come up with some way to remember that this is a value that you plug in for x, but that you don't accidentally, in the process, just kind of forget and plug it into the y, which it looks like a variable, right? X, Y, Z, it feels like a variable. And it is easy to accidentally whoopsie and plug it in for the y. So my little workaround, little personal hack is I don't just write down 1 or 0. Right? I write down x equals 1 to remind myself, because I do not trust myself. Right? That gets plugged in for x, not for y. That make sense to everybody? Okay. Y'all have a good rest of your day. We will see you on Wednesday. Have a good one. Don't forget about attendance if you didn't already get checked off.